We are now going to examine the MNIST database. This database is a very good way of looking into classification problems. Classification problems are when you wish to have an algorithm determine if the values given and the record given is of a couple of specific classes. In other words, it's not continuous. In the MNIST database, the correct answers can be anywhere between 0 and 1, only being whole numbers. Thus, it is not continuous and is a classification problem. To do this, first we will need to get the database. Because MNIST is such a famous database, it's actually already bundled within the sklearn library. Simply use the code here and it will already be downloaded onto your program. Here we make x and y, x being a list of vectors, which is of itself a vector. Each vector contains pixel data determining the darkness of the pixel represented. The y value represents the corresponding labels that correlate to the vectors in the x vector. When it comes to looking at the database, simply typing either the x or y will output what is inside each array, whereas typing shape behind it will tell us how much is in each array. For example, here we have 770,000 different vectors, each having 784 sets of pixel data each. If we wish to see what each pixel data is, we can use the following code and use matplotlib in order to plot each pixel and its corresponding darkness. As we can see here, this is something we would take to be a 9. Now then, why should we split the database? Well, quite simply. When a database is set up, you might have 100,000 values. However, this can be problematic, as if you train the model on that 100,000 values, it will now be fit to that model specifically. And if we give it new values, we won't know how accurate it will be, because we'll have to retry it and get the new data. This can be very cumbersome. So instead, before you start creating a database, it is best to separate and create a training set and a testing set. The testing set will be put off to the side until the very end in order to validate the tests, while the training set will be used in order to create and craft the model. In this instance, we are going to use a binary classifier. Think of a binary classifier as a light bulb. It can either be on or off. For example, in this image, it shows a 9. If it was correct, the binary classifier would be on if it was a binary classifier for if it was a 9. However, if it was a binary classifier for if it was a 4, it would be off, or a 0. In order to create this, we simply need to take all the Y training data, which is our correct values, and only get the data in which it is a 5. We then take that with the testing data and do the exact same. This will make sure that we only correct true for when it is a 5 that is correct. The best way to go through and create a binary classifier in this instance is a stochastic gradient descent model. Stochastic gradient descent is like all other bits of gradient descent, except because it is stochastic, at every new piece of record that it trains the model on, it will reset the hyperparameters to the new values. Thus, it can be said to be training in epochs. Once we have fitted it to the data by using this algorithm right here, fit, xtrain, and ytrain 5. Remember, we have created ytrain 5 in order to only return true when the training set is a 5. In all other instances, it will turn false. It will then, after being fit, predict new data, some digit. We can see here it is set to false. Remember, we are testing to see if this picture is a 9. Thus, it is correct that it returned back false. However, how are we to validate that this formula is correct over a large set of data? There are two parameters we can use to examine it: precision and recall. We can think of precision as the number of correct answers that it gets. In other words, if a doctor wanted to get the number of cancer cells he got correct, he would be looking at the precision if he got 98% of all the cancer. It didn't matter if he also got 20% of all the non-cancer cells, because he only cares about how much of the correct answer he got. Recall, on the other hand, is the percentage of correct answers. For example, when operating on an eye, a doctor would want to be very careful to get as much recall as possible and not destroy as much of the false positives as possible. In other words, the surrounding eye. He only wants to get the correct answers. These two variables are in constant conflict with each other, because in order to get higher precision, in other words, to get as many correct answers as possible, it must also let in more incorrect answers. Thus, it will have a lower recall. Striking a correct balance between recall and precision is important. Once again, going back to the cancer example, it is much better to have higher precision and get more false positives than it is to get more false negatives, because unchecked cancer is very bad, while as one extra trip to the doctor for a false positive might hurt you for a bit of time, but it's not going to hurt you in the long run. Just to refresh, true positives are when a value is given as the correct answer. In other words, with cancer, is this cancer? Yes, it is. Oh, and the machine got it right? Well, that's a true positive. A false positive would be when it says, is this cancer? It is cancer, but oh wait, it's not actually cancer? That's a false positive. Once again, let's take it one more time with a false negative. If this thing really is cancer and the model says, no, that's not cancer, then that would be a false negative because it guessed incorrectly and it didn't say it was true. It said it was false. This could be very bad in the case of cancer. So we want to have the precision as high as possible. Now, how do we create this precision versus recall state? Quite simply, we would first off predict over a very big training set, as shown here. We have CV. Don't worry about CV, but it simply stands for cross-validation. It's unnecessary to know, just know that setting it to 3 will help you in this scenario. After we have created this prediction over a large set of data, we will then get this, true, false, false, and etc. What this is basically saying is that it thinks the first example is true. It thinks the second example is false. Now, how does this help us? Well, we can take these guesses right here, this is our guesses, and then we can compare it to Y train 5, which is our correct answers. Remember, it will only be 5 and therefore true. So we would see true if it was 5, and we would see false if it was not 5. And we get this right here. This is our scatter matrix. As we can see up here in the comments, this is our true negatives. This is our false positives. This is our false negatives, and this is our true positives. As we can see, it gets far more true negatives than anything else, and it gets a lot of true positives as well. However, we can also see that it gets many false positives, with 687 of the entire things that are guessed to be 5s not actually even being 5s, while as it has a very big problem with false negatives, where 1,891 of what are actually 5s are said not to be 5s. Therefore, we could work on tweaking the parameters, either A, getting more of those things that it doesn't know are 5s into the true positives category, but also increasing the false positives category, or getting rid of as many false positives as possible, but also this will decrease our true positives category. Therefore, we need to keep this in mind. Overall, let's suppose we just want to get the best balance. We don't care if it's precision versus recall. We just want to get as little in each of the two categories of false positives and false negatives as possible. We can do this by using a precision score. Specifically, sklearn already comes with the parameters you need and methods to do it all on your own without having to do any of the math yourself. Simply use this method, precision score. Put your training labels, I should say, that are the trues and falses of if it's 5 or if it's not 5, and then your guesses in the second part. As we can see, it has a precision score of 0.83. It's actually pretty good. While as we see the recall score is 0.65. Now, this, as I said before, is not an overall which one's better and which one's worse. This is simply the precision score of 0.83 and the recall score of 0.65. How can we merge them together? Well, we can use the F1 score. The F1 score is a very fancy way of basically saying we want to take our precision score, we want to take our recall score, and we want to combine them. But specifically, if we have a really bad recall score of, per se, 2, or a really bad precision score of, per se, 5, we would want to make that strike against the formula far more than it would if it was a 60 and a 70. Thus, it has a harmonic mean, meaning that the closer it is to the mean of each one, it will not penalize the score as much. However, if it's further away, it will further penalize the score more and more. Therefore, it will only perform best if both the precision score and the recall score are very high. Now then, we've talked about why you might want to change the threshold, and we've talked about why you might want to value precision over recall. Let's now talk about coding and representing the recall and precision in a graph. If we see here, we are going to create a cross-validation prediction using the decision function. Using that, we'll then get the precisions and the recalls with also the thresholds by using the precision recall curve. We'll pass in our correct values, aka is it a 5? If yes, it's true, else it's false, and then we'll pass in the rest of the scores, aka anything else. Now then, when we define this method, precision, recall versus threshold, we're going to basically be creating a chart, and then we're going to be graphing the lines on said chart. First off, this right here, precision plot, is going to be this right here. And it's going to be putting the precision just like that. This thresholds recall -1, G label label recall is going to be used for the downward sloping line here. It's important to notice that B dash is used for a dotted blue line, whereas G dash is used for a solid green line. Writing the label as X threshold gets us this label right here. And finally, the legend location puts it right here. This helps it put it in context and helps us really understand the correlation between precision and recall and how increasing one will always decrease the other. However, there is something quite interesting you might have noticed, and that's this dip off right here. The reason for that is quite simply because as you get to the last few digits, or as we shall say, the last 6 or so, is it a 5 or is it not a 5? The percentage of correct values changes drastically by just changing one value. If you move the threshold a little bit over, you'll notice that the entire thing will go from perhaps an 80% correct to a 60% correct, simply because one of the 5s is no longer being correctly done. This will cause this jolting effect right here. And you don't want to be there. Make sure you always get your value before and along this curve right here. Now then, we're going to talk about the ROC curve. In other words, we're going to be plotting the true positives against the true negatives, or the false positives, as we can see right here. The goal of the ROC curve, summarized simply, is to stay as far to the top left as possible. This is where we want to be, the perfect balance right here. So specifically, when we plot the ROC curve, what it is, it's just the true positives rate versus the false positives rate. That's it. This is not fancy math, unlike up here. Just simply plot it and see what you get. It's wonderful, and you should use it. It's very good. Now then, we're going to talk about 3 different types of multis: multi-classes, multi-values, and multi-labels. We're going to get to the other 2 later, but let's talk about multi-classes because they're actually quite interesting, and they take what we currently know and twist it a bit. So we have a binary classifier. It can either be 5 or it can't be 5. What if we were to be a little bit more resource manageable or resource less intensive? What does that mean? Basically, instead of saying each digit of each possibility gets its own binary classifier, let's say it's either 5 or it's either 4. It's still a binary classifier because it can either be on or off. On being it's 5, off being it's 4. Now what's the point of this? Well, quite simply, we can take the confidence levels each of these binary classifiers get, and then we can say this one has the highest confidence, therefore it's what we're going to choose. What does this mean? Well, let's go with OVA. This is what we've gone with so far. It's either that class or it's not that class. It's a 5 or it's not a 5. However, multi-class classification uses OVO, or 1 versus 1, whereas OVA is 1 versus all. 1v1 is it's either a 5 or it's either a 4. It's extremely efficient and much quicker to train. However, because it doesn't have an on-off as in 5 or not 5, instead it's 5 or 4, it is not as good in the long run as is it a 5 or is it not a 5. However, in most cases, you're going to be using OVO. One example is the stochastic gradient descent. When you do it, you'll actually automatically be using OVA automatically. Sorry, I flipped it. OVA is going to be used automatically no matter what. Using stochastic gradient descent, it doesn't even ask you if you want OVA. It will just always use OVA no matter what. Now then, let's create some of these things right here. It's stochastic gradient descent. We'll make a decision function, and it's going to use these sum digits, and it's going to put this out. This is the confidence that it's 1. That's confidence that it's a 0. That's confidence that it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 9 just goes up to 9. And we can see that this is the one it has the highest confidence in. Therefore, it's going to blurt off that, hey, I think this is a 3, because 0's low, 1's low, 2's low, but 3's just right. However, it should be noted that this isn't a 3, so it's actually getting the confidence incorrect. But it's important to notice that this is how it would determine in an OVA scenario. Now then, let's suppose we really did want to use an OVO, even on stochastic gradient descent. What would we do? Well, quite simply, when we use the stochastic gradient descent and we use the decision function, instead of passing this in, we would pass this in parameterized by this class, 1 versus 1 classifier. However, once again, you really shouldn't use it. It's much less effective. It's much less stable than the OVA, but it is quicker. But don't use it. Just use OVA at all times, and it'll do it automatically, OVA. Once again, let's use a random forest to predict what values the images has, because it is a little bit better. Using this, we can then cross-validate the scores using said model, using the training data, using the training labels, and cross-validating it 3 times, scoring for accuracy. Using that, we can get this. Each of the 3 times it trained on the cross-validation, it got 0.87, 0.87, and 0.88. This is entirely different from everything else. This is something the computer does on its own. It uses a self-scoring system we specified as accuracy. We could change it to precision, and we could change it to recall, but we're using accuracy for the sake of learning about it. This 0.87 is actually quite good, and we can see it's consistently 0.87, 0.87, and 0.88. So we have a good model here. Now then, we can make it actually better without doing much work. Quite simply, if we have different values that have different ranges, for example, this one can be between 1 and 100, or this one can be between 2 and 3, and we try to compare them to each other, they have different scales, and thus they'll affect it differently. The one with a higher number will affect far more than the one with the lower number. We can do this by scaling everything to be the same scale between 0 and 1. In fact, 0 and 1 is what we should be aiming for. Even if it's all one scale of 0 to 100, we still want to scale it down to 0 to 1. And to do that, we'll use the standard scaler. It's recommended at the end of every time you're preparing the data, you use the standard scaler. And it's very simple. Import the class, create the class, and then fit transform it to whatever the data is. Just pass in the xtrain, and then specify the type you would like it as. When we do this, we'll notice it goes from 0.87, 0.87 to 0.88 to 0.89, 0.89, and 0.89 consistently. It's a slight improvement, but it is going to be drastic in the long run. So make sure you consider using standard scaler at the end of every single bit of machine learning stuff you do. Now then, this is helping us get more accurate. However, how would we learn how to get less wrong, as you'd put it? Well, quite simply, we can predict the correct value. We can use a prediction to get the values and then use a confusion matrix to see how they stack up against each other. We do it here. We just use cross-validation predict, and then we create the confusion method matrix like so and then print it out. Now, this is basically saying the number of times it gets it whenever it says it's right. To put this down here, when the correct value is 0, it guesses 0 this percentage of the times. The lighter the square is, the better it is. Whereas whenever it is 0 correctly, it guesses 1 that many times, or 0, as we can see up here. The darker the square, the less it guesses it. Now we can see that in general, it doesn't really guess any numbers incorrectly. However, it does guess some ones less correctly more often. For example, it guesses 1 right here, often, most of the time. However, if we look at 5, it's gray a lot. Therefore, while it might not guess that the 5s are any other numbers a lot, it might miss a lot of 5s. We can look at correcting that later on. In fact, right now even. But let's look at what we would do to see how many incorrect guesses it guesses that would be false positives. So if we just simply flip it around to where we're on the opposite side of it now, and we fill the diagonal, because after all, it's going to be crazy every single time of pure white. So just fill the diagonal to get rid of it, and we display it, we see this. We see that there are a lot of false positives that have patterns. For example, notice 8. It seems to get a lot of false positives for 8. But notice it's also not the other way around, as for example, all of these don't have false positives this way. It's exclusive to its own row. And we need to look at these numbers to, for example, notice what's going wrong and perhaps see if either A, our data set has a problem where the 8s aren't drawn well, or B, if perhaps our model is messing up on predicting 8 and what we can do to make our model better. Now that we've looked at analyzing errors, we can talk about multi-label classification. We talked about multi-class classification, which is where it can either be 1 or 2, and we talked about binary classification, which is it can be either 1 or not 1. Multi-label classification is basically where it can have multiple correct answers. In other words, let's suppose you had a picture and you wanted to determine if it had a dog or a cat, or it had neither a dog or a cat. If it had a dog, it would be a 1. If it didn't have a cat, it would be a 0. And if it didn't have neither, once again, it would be 0. So it would be 1, 0, 0. And this is what's different between it and a binary classifier. A binary classifier is only one value, whereas a multi-label classifier can have many different labels. As we can see here, it could be 0, 0, 1, 0, 1. This could, for example, say, this picture doesn't have Bob, it doesn't have Jill, it does have Jack, it doesn't have John, but it does have Jane. There are so many different ways you could use this, and it's extremely important, as I said, in recognizing pictures or recognizing objects in pictures. To do this, quite simply, you get the training data, for example, is it larger than 7? So this right here is all the answers that are larger than 7, and this right here is all the answers that are odd. And just like before with how we got all the variables that were greater than 500 and talking about pandas, the overview, check that out if you need to, we can simply create a NumPy array that takes all the values that are larger than 7 and all the values that are odd and combine them. Then we pass that in as a parameter to KNN-CLF fit, and we can fit the model using this parameter of multi-labeled. It will then determine either A, is it greater than 7 or less than 7, yes or no, which will be a 1 or a 0, or it will determine if it is odd, therefore it will be 1 or 0 odd. For example, let's take the number 3. For the first label, it would be a 0 because it's not 7. For the second label, it would be a 1 because it's odd. This is very useful, as we've said before, with photos. Now then, let's take multi-output classification, the final thing we're going to talk about. Multi-output fascination is no longer, is it 1 or is it 0? It's now, is it 1, is it 0, is it 2, 3, 4, or 5? You can make it whatever you want. This is very useful, of course, when something can be so many different things, just like binary classifiers. In fact, multi-output classification, behind the shell that you might not know, is actually just binary classifiers stacked on top of each other. However, for our purposes, it's not necessary to know that. Just know that multi-output classification is used when you want to have multiple classes have multiple outputs. For example, here we can see we have data. We add noise to it. So now we've got the modified thing. It's got the noise in it. Then we're going to add the test data. The train data is here. Test data is here. We've added noise to the test data. Now we're going to modify the y training data to be equal to the x training data and the y test modification to the x test destination. Basically what we're doing is we're taking what the number should look like, a pure number, which is the training data, and we're setting it equal to this garbled image. It's going to look like the data, but it's going to have random fluctuations of extra black pixels, if you like to put it, or darker pixels at random intervals. The reason for this is to simulate, for example, a messy piece of paper or a bad read-in. We can then fit the data and then clean the digits using this data right here. What does that mean? Well, basically, in terms of multi-output classification, it's going to use this prediction, KNN, which we haven't gone over, a very strong neural network, to take the training data that's been modified and then take the y training data that's been modified, aka the clean digits. So the clean digits, it's going to take the muddy digits and it's going to train it. And then it's going to be able to predict how to draw the digits. It's going to guess, and it's going to go, this is a muddy digit. Yeah, that digit should be off, so we're going to turn that pixel off. That pixel should be lighter. We're going to make that lighter. That pixel should be darker. We're going to make that pixel darker. And it's going to do this continually. And it's going to be multi-output because it's going to change every single pixel at the same time. Thus, it's going to have a pixel value of 0 to 255 because that's the pixel values each one can have. And that's a very good example of a multi-output classification because it can be anywhere from 0 to 255. I hope this has helped you out a lot. Just to go over it again, you get the database very specially from inside sklearn. Very easy to do, and a lot of your databases will be from sklearn. Then you'll look at the data set, looking at your labels and looking at the shape of your data. Finally, you can look at what the actual data looks like by putting it out with matplotlib. You can split the data set as you should. 70% should be your training data, 30% should be your testing data. Use the binary classifier. It's either on, aka it's a 5, or it's off, it's not a 5. Very basic, and you will use it quite often. Use stochastic gradient descent to, of course, slowly get that binary classifier to the best of the best. We've talked about this in other lessons, and the reason why is because stochastic gradient descent is the go-to loss function used to train models. Once you've got it, you're now going to validate your classifier. You've gotten this model. It can say it's either a 5 or it's not a 5. And you're going to check, and you're going to see, okay, it gets this many true positives, it gets this many true negatives, and it gets this many false positives and false negatives. I don't like how many false positives it gets, so therefore I'm going to back up on the threshold. It's going to, of course, get you less false positives, but on the other hand, it's also going to get you more false negatives, which is, of course, maybe good, maybe bad, depending on what you're doing. Once again, with cancer, for example, you would want to back that threshold up like crazy. That way you get as little false negatives as possible. Even though you'll get many false positives, that doesn't matter because getting false negatives is far worse. Then we talked about the Roc curve. Basically, when you plot true positive values versus true positive rates, false positive rates, you want to be on the top left as much as possible. You want to be around right here. Then we talk about multi-class classification, which is one of 3 multis: multi-class, multi-label, and multi-output. Multi-class can be thought of as having it either 1 or 2. It's still binary, however, instead of being on or off, 1 or not 1, it's 1 or another class 2. As for multi-label, it can have multiple labels. It can either be 1 or not 1, 2 or not 2, 3 or not 2, and that can all be one classifier. Or it can even be 1 or not 2, 3 or 4, 5 or 6. That's another way you could do it. And you could have it be a multi-class, multi-label operation. However, Let's suppose we were to talk about multi-output. That means that your classifier can put out any number, not just 1 or not 1. It can be anywhere from 300 to 400. You can decide. We then talked about error validation, or error analysis, basically looking at what it gets wrong and what it gets right. It gets these numbers a little bit less right than it gets these numbers, and also how it gets these wrong. It gets 8 wrong like crazy. Perhaps this is something we should look into. So this is an overview of what this lesson has talked about. I hope you've enjoyed it, and I hope you've learned a lot.